to solve this differential equation, what I would do is I would assume the solution that x of t equals c e to the pt. And then what I would do is I would take that solution and I would plug it back into here. And when you plug it back into here, what you find out is this is the most general solution. So I encourage you to do that at home. All right, make sure you can get to this at home. All right, but what's not so obvious is that this answer, while it's the correct answer, it's not so obvious what it is. All right? So you can get this by doing a little bit of trig algebra to get this solution is exactly the same thing as this solution. And you do a little bit more trig algebra, and you can see that these two solutions are exactly the same thing as this. Okay, so the big point is these three solutions are just the same thing. They're different representations of the same solution. And why do you think I gave you three different representations of the same thing?
So you can learn it better.
What's that?
Learn it three different ways.
How about this? Why do you have Cartesian, spherical, and cylindrical coordinates?
Which system's working?
Because you look at the system and you say, which one works best for me? All right, so when we're going to answer a problem, when we're going to solve a problem, we're going to say which solution helps us the most. All right? And so that's why we want these three answers right here. Okay. So that's our harmonic oscillator, which is a review. But notice this differential equation, and then look over here at this differential equation. They're the same thing, right? One's just, the differential equation doesn't care that it's derivatives with respect to x or derivatives with respect to time. They're the same thing. All right? Now, in this case, omega naught was 2 pi over t. And notice these were time derivatives, so that this constant came out to be an angular velocity, radians per second. Over here, what is the derivative? Is it with respect to space or with respect to time?
Space.
Space. So what do you think this is going to equal? It's going to equal 2 pi, but it's not going to be a period t. The period had to do with the time.
So it's going to be per meter.
Okay, it's going to be per meter. And what do you think is related to these two things with a period or something? It's something that has a length,
Wavelength. Yeah.
Okay. 2 pi over lambda. And this is what I call a spatial velocity. Spatial angular velocity. So if I call this the angular velocity, I call this the spatial angular velocity. It's how much this function is changing with respect to the wavelength. Okay, further, what are the answers to this differential equation?
Same as
Okay, so let's modify this. Let's modify it.
not would actually be
So this is not going to be x of t, this is going to be
side of
psi n of x. And what's it going to equal?
C plus I K Q is
K, then what? Is it going to be a t? It's going to be x. Plus, there you go. So no big thing to worry about. Down here, what do we have?
plus omega naught with kx. Omega naught t with kx.
That's going to be kx. This is going to be kx. And the last one, just kx, yeah. There we go. Okay, so up until now, everything's entirely general. Almost every problem you go through, it's going to go through the same steps. You're going to end up in the same place. And what's the only thing going to be different from problem to problem? Is V, so the K. All right, so all these problems are always going to come down to look like this. Okay, let's now solve our particular problem. All right, so we're going to solve our particular problem. We have these solutions.
And in our particular case, V is 0. So
Yeah, very good. So let's solve our particular case. The infinite 1D well. Okay, and you're starting to look at it. You're starting to look at what do we know about our well?
V is 0.
V is 0 where?
Got it, what's on
Okay, inside. But remember when I solved that other differential equations, I looked at the boundaries, and the boundaries were the things that helped me solve for those constants. So when I look at the boundaries here, what boundaries am I probably talking about?
0, right?
The potential equals 0. Oh, I jumped ahead. Sorry. All right. We know specifically in region 2 that what is the potential?
0.
0. Okay. So in our case, our particular case, K equals the square root of 2m over h bar squared En. Alright, so we know that. Alright, but now let's go to the discussion that I was just having. Let's now solve for psi n. And to solve for psi n uniquely, we need to figure out what these constants are, C1 and C2. And that's when we want to look at the boundary conditions, right? So our boundary conditions that we're interested in this problem are the potential equals 0, the wave function. Now,
0,
so I keep saying the potential. But what do we need the boundary conditions on now? The potential or the wave function? We need the potential on the wave function because that's what I'm solving for here. So what do I know about the wave function at some of the boundaries?
0.
That equals 0 where?
X equals down, X equals A.
That's right. Okay, so I know that the wave function equals 0, and x equals 0, and x equals a. So I know, so by inspection I can see that the side of x equals 0 and x equals a, that it equals 0. So when I'm looking at these equations, what I do is I say, okay, which equation is going to help me most with solving these boundaries? And the answer is the second one, right? Because when I put in x equals 0, I still have C1 here. But if I put x equals a, I still have C1s and C2s. But check out what happens with when I use number 2. So I'm going to try this one. Okay, so let's try psi of x equals 0 in equation 2 is going to equal C1 sine of 0 plus C2 cosine of 0, and that all has to equal 0. Okay, that means C2 is 0 because sine of 0 is already 0, so that goes away. Cosine of 0 is 1, so we have C2 equals 0. Okay, so we just got C2. All right, let's try the next condition. Sine n of x equals a, and that's going to be now C1 sine of k times a. And what does that have to equal? 0. That has to equal 0. All right? So that could mean two things. It could mean that C1 is 0, all right, or that sine ka is equal to 0. Now, if I have C1 equal to 0, what does that tell us our wave function is? 0. So that doesn't tell us anything. So let's go with the other conditions. All right, we haven't determined C1 yet. But what we do know And why doesn't that bother me right away? About a constant in front of this that I haven't solved yet. Why aren't I worried about that particularly?
Because it's a constant.
It's a constant, and then how else do I handle the things that come in front of wave functions? What else, what do I ultimately have to do with my wave function? To make it satisfy the Born postulate.
Normalize when.
I have to normalize it, so what am I going to end up doing in front of this wave function anyway?
Put in a constant.
I'm going to put in some other constant that normalizes the function, and so I'm truly not even worried about that one. All right, so I'm essentially done. Okay, so I'm going to worry about this, worry about later what I have to normalize. All right, and so the real problem then is what then is necessary is that sine Ka equals 0. And what does that mean? What conditions make this true?
That Ka equals something to times pi.
Okay, so it means that Ka has to equal
N times pi.
n times pi, all right, where n can equal,
Any natural number.
okay, 0, 1, 2, dot, 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 0, 1, 2, 3. All right, so I'm going to erase all this stuff, all right, except for the very beginning stuff. Because we've essentially solved this problem. All right, we've essentially solved for our psi n's of x. Our psi n's of x equals some constant c times sine kx's, where k's equal the square root of 2m over h bar squared en. All right, and we also know that k times a has to equal n pi, where n equals 0, 1, 2, 3, and so on. Okay, so let's see what's going on here. What I'm also saying from this is that k has to equal n pi over a. So now if I throw that back into here, what I find is that n pi over a has to equal the square root of 2m over h bar squared en. Or that n squared pi squared a squared has to equal 2m over h bar squared en. Or that en has to equal what?
N squared pi squared h bar squared.
N squared pi squared h bar squared, all divided by 2 m a squared, for n equals 0, 1, 2, 3. So what did we just solve? We solved 1. We solved for our wave function, right? For all but the normalization constant. And 2, we've also found the quantized energies.
N equals 0 and 0 goes to
Okay, so yeah, that's one point that I wanted to mention. I'm glad you brought it up. So we could write this, what I should have done is when we found the condition on Ka equals n pi, I could have put a little subscript Kn, all right, and then Kn, all right, so that what we found out is that Kn equals n pi, all right, so for this, the most general solution should be sine Kn of x. And as Bradley pointed out, for n equals 0, you would have psi 0 So size